Chemistry Paper 2 exam. Dear students, you are warmly welcome in this solving session. For calculations, you may use the following constants. Gas constant, denoted by letter R, the value of it is 8.31 joule per mole per Kelvin, or 0.082 atm per mole per Kelvin decimeter cubic. Ionic product of water at 25 degrees centigrade, Kw, is equal to 1 times 10 raised to negative 14 mole square decimeter cubic raised to negative 6. Standard pressure which you may use in your calculation should be equal to 760 millimeter of mercury, or equal to 1 times 10 raised to 5 Newton per meter square, or equal to 1 atm. Standard temperature which may be used, or which you may find it important to use in your calculation, should be 273 Kelvin. Also, 1 Faraday should be equated to 96,500 coulomb per mole. Atomic masses which you may find are of importance to use include atomic mass of hydrogen equal to 1, atomic mass of carbon equal to 12, atomic mass of nitrogen equal to 14, atomic mass of oxygen 16, chlorine 35.5, sodium 23, and barium atomic mass to be used should be equal to 137. Let us start with first question of this Chemistry 2 examination paper. Question 1, it contains 4 parts. This is different from Chemistry 1, where a number of asked items were 3 parts, part A, B, C. But in Chemistry 2 exam, a number of items asked are from part A, B, C, and D. Question 1, part A, and it is the first item. In the first item, and in part A, we have 2 items again, sub-items, question Roman 1 and question Roman 2. Let us start with part A, and specifically with Roman 1. Explain why solutions exhibiting negative deviations from Raoult's law form lower vapor pressure than that of pure component. So we need to account for this observation. Roman 2. Solutions containing chloroform and acetone show negative deviation from Raoult's law. Explain this observation in terms of molecular interactions. And item Roman 3, it asks, ethanol and cyclohexane solutions show positive deviations from ideal behaviors. Explain in terms of differences in the structures or polarity of the 2 components. Let us start with part 1, where we need to give the account of why there are some solutions which show a negative deviation from Raoult's law. What Raoult's law is all about. When you mix the 2 solutions and you need to define the pressure of individual component in the solution, or the total pressure of components in the solution. This can be well described by Raoult's law. It describes the behavior of solution in terms of vapor pressure, and it is the vapor pressure of each component in a solution. We need to remember that when we have two individual components, one of it is solute and the other component can be termed as a solvent. A solute, if it is non-volatile solute, it tends to lower the vapor pressure of the solvent. In here, we should refer to the molecular interactions. How these molecular interactions work, that's why we see this deviation from Raoult's law. But all in all, let us first state what is Raoult's law, and then we are going to see how this molecular interaction affect the overall pressure of the component in the solution or the pressure of individual component in a solution. From Raoult's law, we can state it as total pressure developed above the solution is equal to mole fraction times partial pressure of the first component, that is component A, plus pure pressure of component B times it is mole fraction. But each term with pure pressure and mole fraction is defined as a partial pressure. Volatile molecule in the solution, they have a tendency to escape above the solution, and when they escape above the solution, they create pressure above the solution. This is the result of intermolecular interactions. If molecules are held together, it means intermolecular forces between the molecule is higher. There will be a lower tendency of volatile molecule to escape and go to a phase above the solution. And if the molecular interaction are lower, there will be a higher tendency of molecule to escape and go above the solution. So why these components show deviation from Raoult's law? It is due to the kind of intermolecular interaction existing in solution components. Again, from Raoult's law, an ideal solution, it is total pressure is given as P total equal to partial pressure of component A plus partial pressure of component B. Partial pressure have been defined. For solution which deviate from Raoult's law, they are so-called solution which show a negative or positive deviation from Raoult's law. Total pressure can be greater than the partial pressure of individual component, that is a positive deviation from Raoult's law. And if partial pressure is total pressure is less than the partial pressure of individual component, the type of solution is the solution which show a negative deviation from Raoult's law. Again, from the term partial pressure, to calculate it, you need to take the pure pressure of component, either A or B, times it is mole fraction. But what is mole fraction? Mole fraction is equal to the number of mole of either component A or B divided by the total number of moles. This is the mole fraction for component A, and in the next slide we can see how a solution which deviates from Raoult's law negatively, it is the expression should be as total pressure developed above a solution is less than the partial pressure of individual component A and B. Thus, solutions which show a negative deviation from Raoult's law behave in such a way due to the fact that there are greater intermolecular forces of attraction in the solution than the attractions between the pure liquid molecules. In that case, fewer molecules tend to escape. This leads to a low vapor pressure above a solution. And you can say further as intermolecular forces in component A and in component B as a pure component is less than the intermolecular forces between component A and B. Roman 2. Solution containing chloroform and acetone show negative deviation from Raoult's law. Explain this observation in terms of molecular interaction. We need to refer to the molecular interactions, and therefore from molecular interaction we need to explain why solution containing chloroform and acetone show negative deviation from Raoult's law. In a solution containing acetone and chloroform, as you can see the structure, acetone and chloroform, they form hydrogen bond between themselves as shown below. This is the acetone molecule with 3 carbon and carbon to oxygen double bond. From a chloroform, 3 chlorine atom, 1 carbon atom and hydrogen atom. Between hydrogen in the acetone molecule and hydrogen from chloroform molecule, there is hydrogen bond. The moment molecules need to escape to form a vapor pressure above a solution due to hydrogen bond, the tendency of molecule to escape become lowered. Since the tendency of molecules to escape have been lowered, this result to a low vapor pressure above a solution. That's why we're going to see the vapor pressure of the solution is less than that of the expected from Raoult's law. Part A, and we are in Roman 3. Ethanol and cyclohexene solution show positive deviation from ideal behavior. Explain in terms of differences in the structure or polarity of the two components. Again here, we are still referring to the intermolecular forces operating between the two mixed components. Yes, we find that ethanol molecule, between ethanol molecule, there is a hydrogen bond. It means ethanol molecules are bonded strongly by hydrogen bonds. In pure cyclohexane, this is a nonpolar solvent, and the kind of interaction is induced dipole interaction or dispersion force. and such kind of molecular interaction is very weak. And in here we need to define a scenario where ethanol and the cyclohexane have been mixed together. In a process of mixing cyclohexane and ethanol, we see that cyclohexane, we see very weak forces between them occur in the way of ethanol interaction. That's why the bond between ethanol molecules become weak. It means cyclohexane break the hydrogen bond or obstruct the hydrogen bonds, and hence ethanol molecules together with cyclohexane molecules, they will have a higher tendency of going to above the solution. This will result to the reduction in ethanol intermolecular interaction, that is hydrogen bonding, and hence the vapor pressure of such solution will show a positive deviation. This means that a higher vapor pressure will be formed, which is contrary to that which is expected from Raoult's law. Part B. This is the question which we need to solve 2 items, but before that let me read the question. The vapor pressure of ethanol and methanol are 44.5 millimeter of mercury and 88.7 millimeter of mercury respectively. An ideal solution is formed at the same temperature by mixing 60 grams of ethanol with 40 grams of methanol. Roman 1, calculate the total vapor pressure of the solution. Roman 2, calculate the mole fraction of methanol in the vapor. From the stated equation, important data are pure pressure of ethanol and the pure pressure of methanol. Pure pressure of ethanol is denoted as P naught ethanol, which is equal to 44.5 millimeter of mercury, and pure pressure of methanol, P naught methanol, is equal to 88.7 millimeter of mercury. Mass of ethanol given is equal to 60 gram. Mass of methanol given is equal to 40 gram. And we need to consider or to remember the molar mass of ethanol and methanol. Molar mass of ethanol is equal to 46 gram per mole. This is from summing the atomic mass of each atom in the molecular formula. Molar mass of methanol is 32 gram per mole. And from this data, we need to calculate the total vapor pressure of the solution. And from this question, we need to refer to the general formula from Raoult's law. When you mix 2 individual components, what happened to the pressure term? Will the pressure term increase, decrease, or remain the same? And since we consider the mixing of methanol and ethanol as a mixing which result to the ideal solution, therefore pressure of the solution is equal to partial pressure of ethanol plus partial pressure of methanol. You get the value of partial pressure of ethanol and partial pressure of methanol, and after summing it you get a total pressure of the solution or due to solution. To get the partial pressure of each component, we need to consider a mole fraction term. From a mole fraction term, either of ethanol or methanol, we need to include the mass of individual component divided by its molar mass. Over there you get number of moles of first component, that is ethanol. From the second component, which is methanol, also you are going to use the same approach of taking mass of methanol divided by its molar mass. You get the number of moles of methanol. After getting the number of moles of ethanol and methanol, you can establish a mole fraction, and eventually a mole fraction can be used to calculate the partial pressure. Number of mole of ethanol, as you can remember, the mass of ethanol was 60 divided by molar mass of ethanol 46 gram per mole. Number of mole of ethanol is equal to 1.3043 mole. What about number of moles of methanol? You're going to do the same. Take a mass of methanol divided by its molar mass. Mass of methanol was 40 gram divided by molar mass of methanol 32 gram. Number of moles is equal to 1.25 moles. From this obtained number of moles, it is where you are supposed to find a mole fraction of individual component, either ethanol or methanol. Mole fraction of ethanol is calculated from this expression as mole fraction of ethanol is equal to the number of mole of ethanol divided by the total number of moles. Number of moles of ethanol plus number of mole of methanol. Yes, in here it is where this is mass, this is number of moles of ethanol. Number of mole of ethanol 1.3043 mole. Total number of moles takes the number of moles of ethanol plus number of mole of methanol. The mole fraction of ethanol is equal to 0.5106. Unit of mole fraction. With this term, there is no unity. Remember, mole in the denominator cancel with the mole in the numerator. At this moment, we have a mole fraction of ethanol. Since to calculate a partial pressure of methanol, we need also to find a mole fraction of methanol, but we have a mole fraction of ethanol. We have a general expression which say mole fraction of two components. It means mole fraction of ethanol plus mole fraction of ethanol should be equal to 1. From this part, we have mole fraction of ethanol, and we need to make mole fraction of methanol the subject. What should be the expression? The expression for finding mole fraction of methanol should be equal to 1 minus mole fraction of ethanol. Mole fraction of ethanol was 0.5106. Therefore, after making mole fraction of methanol the subject, mole fraction of methanol will be equal to 0.4894. So these are the mole fraction terms. From these mole fraction terms, we can utilize them to calculate partial pressure of each component, and after doing so, we are going to sum them to get a pressure of the solution. partial pressure of ethanol, as I said before, you need to take the mole fraction of ethanol times it is pure pressure. Mole fraction of ethanol is equal to 0.5106. Remember, it is unitless, times pure pressure of ethanol, which was 44.5 millimeter of mercury. Therefore, partial pressure of ethanol is equal to 22.72 millimeter of mercury. What about partial pressure of methanol? We have the mole fraction of methanol, and it is pure pressure. Mole fraction of methanol was 0.4894, and it is pure pressure was 88.7 millimeter of mercury. Therefore, partial pressure of methanol is equal to 43.41 millimeter of mercury. We have a partial pressure of ethanol and partial pressure of methanol. So then we add the two partial pressure to get a total pressure of the solution. Total pressure of a solution, remember, is equal to partial pressure of ethanol plus partial pressure of methanol, which should be equal to 66.13 millimeter of mercury. Therefore, this was the total vapor pressure of the solution. Item 2, we were required to calculate a mole fraction of methanol component in the vapor. Remember, it is a mole fraction term which we need to calculate. And to find a mole fraction of methanol, we need to consider it is partial pressure and the total pressure of the solution. Therefore, mole fraction of methanol in a vapor phase is equal to vapor pressure of methanol, which is the partial pressure of methanol, divided by the total pressure of the solution. Total pressure of the solution was 66.13 millimeter of mercury, while partial pressure of methanol was 43.41 millimeter of mercury. Now we have these two important data. We need to take partial pressure of methanol to divide with total pressure of the solution. Partial pressure of methanol is equal to 43.41 millimeter of mercury divided by the total pressure of the solution, which is equal to 66.13 millimeter of mercury. A mole fraction term which you obtain over there is 0.6564. Convert it into percentage. The percentage mole fraction is equal to 65.64. Therefore, the mole fraction of methanol in a vapor is equal to 0.6564 or 65.64%. Part C. At a pressure of 760 millimeter of mercury, a mixture of nitrobenzene with the molecular formula 6 carbon, 5 hydrogen, 1 nitrogen atom and 2 oxygen atom, and water boiled at 99 degrees centigrade. The vapor pressure of water at this temperature is 733 millimeter of mercury. Find the proportion of water and nitrobenzene in the distillate obtained by steam distillation of impure nitrobenzene. yes, two component, nitrobenzene and water, in liquid form. They have been boiled at that temperature, and a vapor containing the two component has been formed. And in that vapor phase, we need to establish the proportion of water and proportion of nitrobenzene. First of all, you need to consider this important data. Total vapor pressure of the two component of a mixture is equal to 760 millimeter of mercury. Vapor pressure of water, the first component, is 733 millimeter of mercury. Also, we need to remember about molecular mass of nitrobenzene as well as molecular mass of water. Molecular mass of nitrobenzene is equal to 123 gram per mole. Molecular mass of water is equal to 18 gram per mole. Important question are to find a proportion of water as well as a proportion of nitrobenzene. A proportion of water, it means a mass of water in nitrobenzene, as well as proportion of nitrobenzene, it means mass of nitrobenzene in a mixture which contain nitrobenzene and water. And in here, we need to use again Raoult's law in order to establish proportion of nitrobenzene and proportion of water. Apart from using Raoult's law, also we should refer to Dalton's law. From Dalton's law, we find that the total vapor pressure above the solution is equal to vapor pressure of first component, that was water, and this is summed with the vapor pressure of the other component, which is vapor pressure of nitrobenzene. And we know that from the total vapor pressure developed from nitrobenzene and the water mixture is equal to vapor pressure of water plus vapor pressure of nitrobenzene. Since we need a vapor pressure either of nitrobenzene or vapor pressure of water in order to establish the proportion of either water or nitrobenzene, therefore we need to establish the partial pressure of nitrobenzene. That is the missing data. We have a vapor pressure of water which is 733 millimeter of mercury, and from the total vapor pressure of nitrobenzene can be calculated as total vapor pressure equal to 760 millimeter of mercury minus the vapor pressure of water, which is equal to 733 millimeter of mercury. So this is the vapor pressure of nitrobenzene. But from Raoult's law, we find an important relationship between partial pressure and mole fraction, and from a mole fraction term we can establish the proportion of each component. This is expanded the formula from partial pressure of individual component, that is nitrobenzene. Therefore, this term is a mole fraction term of nitrobenzene and water. Again, we are supposed to divide it by partial pressure of nitrobenzene with partial pressure of water. From this relationship, it is where we're going to establish proportion in terms of mass. From mole fraction of nitrobenzene divided by mole fraction of water, which is equal to vapor pressure of nitrobenzene divided by vapor pressure of water, it can be expanded further to form such a relationship as mass of nitrobenzene divided by mass of water is equal to vapor pressure of nitrobenzene times molar mass of nitrobenzene divided by vapor pressure of water times molar mass of water. From this expression, it is where a proportion between nitrobenzene and water has been established, and simply from their vapor pressure and molecular masses. Partial pressure or vapor pressure of nitrobenzene was 27 millimeter of mercury. Vapor pressure of water was 733 millimeter of mercury. Again, we need to use molar mass terms to find the required proportion. After doing so, we are going to obtain this value of 0.2517 after approximation is equal to 0.25, which is equal to 1/4 in fraction. This proportion is the mass of nitrobenzene divided by mass of water, and a proportion has been established. We started with mass of nitrobenzene, which is equal to 1, and mass of water is equal to 4. Therefore, the proportion of water and nitrobenzene in distillate is 4:1. 3 minutes. Okay. After solving 2 parts of question number 1, therefore let me wind up this session. We are going to continue after a short break.